Welcome to Networking and Health Information Exchange, ISO Open Systems Interconnection, OSI. This is Lecture B. The objectives for this lecture are to explain the concept of the network layer, explain the concept of the data link layer, explain the concept of the physical layer, explain connection-oriented versus connectionless communication, explain the use of network addressing, including security considerations and vulnerabilities.
Slide 3. Additional objectives for this unit, ISO Open Systems Interconnection, OSI, are explain the concept of the network layer, explain the concept of the data link layer, explain the concept of the physical layer, explain connection-oriented versus connectionless communication, explain the use of network addressing, including security considerations and vulnerabilities. Slide 4. The network layer routes packets through the network using network addresses. Internet Protocol, IP, is used to assign IP addresses to network devices. These addresses are used to identify the network devices so that packets can be delivered to the correct device. IP is a connectionless, best-effort delivery protocol. It relies on TCP for reliable, error-free delivery. Slide 5. There are two current versions of IP addresses, version 4 and version 6. IPv4 is the most popular version in use, but IPv6 is starting to be implemented. IPv4 addresses use 32 bits, and IPv6 uses 128 bits. Remember that computers use binary numbers, just zeros and ones. Version 4 addresses are referred to as dotted quad addresses because the 32 bits are broken down into four 8-bit groups called octets, separated by a dot. An example of an IP address using only zeros and ones would be 110010010010011110.111000001. If we convert the binary to decimal, the address would be 192.40.110.225. The IPv4 examples shown in the rest of the presentation are in decimal format because they are easier for us to deal with. An example of an IPv6 address would be 3EEF:4625:7:100:7:7-AE21:57BF. IPv6 addresses use the hexadecimal number system. Slide 6. IPv4 addresses are broken into 5 classes, A, B, C, D, and E. Classes A, B, and C are assigned to networks. Class D addresses are used for multicasting. Multicasting will be explained in a little while. Class E is for experimental purposes. We don't know what's going on with those addresses. The first octet, or first 8 bits of an IPv4 address, determines what class the address belongs to. If the first octet falls between 0 to 127, it is a Class A address. If it falls between 128 to 191, it is a Class B address. 192 to 223, Class C, 224 to 239, Class D, and 240 to 255, Class E. Slide 7. Addresses that have 127 in the first octet are reserved for testing and cannot be assigned to devices. In particular, 127.0.0.1 is reserved for the loopback test. This allows a user to test the TCP/IP settings on a device. Private addresses are addresses that can be used in home, office, or LANs, where the packets do not have to be sent out across the Internet. The Internet uses public addresses. If such a private network needs to connect to the Internet, it must use either Network Address Translation, NAT, or a proxy server. Slide 8. As mentioned, Class D addresses are for multicast. We can classify transmission in one of 3 ways: unicast, broadcast, or multicast. Unicast transmissions are from one source to one receiver. An example would be if you were having a one-on-one conversation with another person. Broadcast is one source sending out a transmission to all devices that are on the same network. For example, a teacher in a classroom is broadcasting their lecture to all the students in the classroom. Multicast transmission is when one sender sends out a message to a group of devices, and that group is identified by a Class D address. For example, if an announcement was made at your college that was addressed to all students in the Networking and Health Information Exchange class, you would pay attention because you are part of the group. Devices are programmed to know what multicast addresses they should respond to. Slide 9. An IP address has two parts. The first part identifies the network that the host with that IP address belongs to, and the second part uniquely identifies that device on that network. For example, if you were driving to 1637 Lawson Street, you would know that the street is named Lawson, and once you got to that street, you would need to look for Building 1637. We know the scheme for addresses because we have learned it. In networking, the subnet mask is what tells us which part of the address is the network and which part is the host. Wherever there are ones in the subnet mask, that is the network portion of the address, and where there are zeros, that is the host portion. 255 in decimal is 8 ones, or 11111111 in binary. In our example, 192.168.12.14 is a Class C address, so the default subnet mask is 255.255.255.0. The first 3 octets identify the network, and the last octet identifies the host. Slide 10. 172.16.0.0 is a Class B address. The default subnet mask is 255.255.0.0. The first 2 octets identify the network, and the last 2 octets identify the hosts on that network. There are 16 bits that can be used to identify hosts on the 172.16.0.0 network. This means we can have over 65,000 hosts on that one network. Not many networks need over 65,000 hosts. We can take the one network and subdivide it, or subnet it, into more networks. We take some of the host bits, zeros, and change them to network bits, ones. If we have a new subnet mask of 255.255.240.0 and we apply to that same address 172.16.0.0, we can create 16 networks with 4,000 hosts on each network. Slide 11. We can then take those subnets and use them for different buildings. For example, if we get a virus on a computer with an IP address of 172.16.32.10, we immediately know it is on a PC in Building B. We could also cut off that subnet from the rest of the network, therefore isolating the virus to just that subnet instead of allowing it to spread to the entire network. Slide 12. Routers operate at the network layer of the OSI model. Routers are multi-port connectivity devices that connect different networks, LANs, WANs, different transmission speeds, media, and protocols to each other. They move packets from one network to another, route packets. Slide 13. Routers choose the best route for a packet to take to arrive at its destination. There are 2 ways that the router knows what the best path is: static routing and dynamic routing. In static routing, a network administrator programs a router to use a specified path to move data between 2 nodes. In dynamic routing, routers automatically calculate the best path between nodes and accumulate this information in a routing table. Routers share information about the routes with each other. A router will look at the destination IP address of a packet, calculate what network it is located on, and based on the information in the routing table about that network, forward the packet to its next hop. A hop is a term used to describe the movement of data from one router to another. For example, if a packet travels across 3 routers from its source to its destination, it is said to have taken 3 hops. As a packet crosses across a router, the time to live, TTL field, in the IP packet is decreased by 1. When the TTL reaches 0, that router will discard the packet and send a message to the sender to let it know that the packet was undeliverable. Slide 14. Internet Control Message Protocol, ICMP, is another protocol that operates at the network layer of the OSI model. Even though IP is an unreliable protocol, it does allow some messages to be sent back to the sender in case there is an error in delivery. Some common ICMP messages are unreachable destination or service, time exceeded, route redirection, and source quench. ICMP is also used with the ping and trace RT, or traceroute, utilities. Slide 15. Ping is used to test if a particular host is reachable on a network and to measure the round-trip time for packets sent from the local host to a destination computer. Ping uses ICMP echo request and echo reply packets. You can ping a device's IP address or its host name. Slide 16. TraceRT, or traceroute, is a utility that is used to trace the route that a packet takes from source to destination. The destination can be referenced by its IP address or name. The output from the command shows the IP address and sometimes the host name of the routers that are traversed as the packet is sent from one device to the other. Slide 17. The data link layer moves frames through the network using physical addresses. The data link layer is the layer where the software and hardware come together. The layer contains two sublayers, the Logical Link Control, LLC, and the Media Access Control, MAC. The LLC sublayer interacts with the network layer and identifies what network layer protocol is being used. This information allows different network layer protocols to use the same network interface and media. The MAC sublayer interacts with the physical layer. It provides data link layer addressing. Slide 18. A MAC address is a unique address assigned to most network interface cards, NICs, by the manufacturer for identification. This is also known as the physical address. MAC addresses are in hexadecimal format. It contains 48 bits, or 12 hex digits. The first 24 bits, or 6 hex digits, are called the Organizational Unique Identifier, OUI. Each vendor that produces NICs is assigned their OUIs by the Institute of Electrical and Electronics Engineers, IEEE. The remaining bits are unique for each OUI and are assigned by the vendor. Slide 19. The MAC sublayer determines how data frames are placed onto the network media. Which device gets to talk? There can be multiple devices sharing the same media, and there has to be a system in place to decide which device gets to place its data on the network. The two MAC methods for allowing access to shared media are controlled and contention-based. Controlled access is also referred to as deterministic access. There is some mechanism that determines when a device can transmit. Each device must wait its turn to transmit its data on the network. Only one device can communicate at a time, and because of this, there are no collisions. Collisions occur when multiple data transmissions interfere with each other, causing none of the transmissions to be good. Token ring and FDDI, or FDDI, are technologies that use controlled access. Slide 20. In contention-based systems, devices can transmit at any time. Collisions may occur. This method is also called non-deterministic. There is no mechanism to decide when a device can transmit data, but the devices have to contend with each other to access the media. Ethernet and wireless are technologies that use contention-based access. Slide 21. Ethernet uses Carrier Sense Multiple Access Collision Detection, CSMA/CD. The device that has data to send will listen to the media to see if there is any signal being carried on the media. Remember, media is the cable carrying the data. If there is a signal on the media, it means that a device is already transmitting data, and that device must wait and try to send its data later. If there is no signal, the device can transmit the data by putting a signal on the media. It may happen that, at the same time the device transmits its data, Another device doesn't hear a signal on the media, and it transmits too. In that case, there would be a collision, causing both signals to become corrupt. The devices would detect the collision and know that they need to send the data again. They would both start the process of CSMA/CD again. Slide 22. Wireless technologies like the 802.11 standards use carrier sense multiple access collision avoidance, CSMA/CA. The device that has data to send will listen to the media to see if there is any signal being carried on the media. If there is a signal on the media, that device must wait and try to send its data later. If there is no signal, the device will send out a signal notifying the rest of the devices using that media that it is getting ready to send out data. This avoids a collision because other devices will not transmit. After issuing the notification, the device then sends out its data. Slide 23. Frame relay, PPP, and ATM are data link layer protocols that are used on WANs. Switches operate at the data link layer. Slide 24. The physical layer transforms bits into signals to be sent across the network media. This is the layer at which data is actually transmitted across the network media. It is commonly referred to as PHY. At the physical layer, we have the specifications for hardware like network cables, connectors, wireless radio transceivers, etc. This layer is also responsible for data encoding. This is the process of taking the data, zeros and ones, and turning it into an electrical, optical, or wireless signal that is transmitted over the media. Popular encoding methods are non-return to zero and Manchester. Topologies are how network devices are connected to each other. Part of the topology involves the type of media that is used, so the physical layer is concerned with this. Slide 25. This concludes ISO Open Systems Interconnection, OSI. We have covered the TCP/IP and OSI models, the layers for each model, and associated protocols.